Okay. Oh, sorry, earthquake. All right, so if the sun is out, this is section 2.3. If the sun is out, then the weather is good. So what kind of statement did we learn this to be?
A if-then or conditional statement.
That's right, if-then statement or a conditional statement. And since everybody's got a plus, I don't have to remember names.
Yeah.
Hey.
But I'm still probably going to say your name. Who said that? Thank you, Cameron. So this is a conditional statement or an if-then statement. And so what we want to do is we want to think about this as a variable. All right, so we're going to just label this as variable P, and we're going to label this as variable Q. All right? And so that being the case, we could rewrite this conditional statement as if P, then Q. Everybody agree with that? Just another way to rewrite it if we assign variables to that. And so this would be a shorthand way. I want to make sure you understand this notation for me to write that. So if you say P, if you see P with an arrow pointing to Q, then you know that translates to if P, then Q. Okay? And so then if we're using symbols, this is our original conditional statement, right? Then I could write the converse of that as,
If Q.
right? Q arrow P, or, like you said, if Q, then P. So it's a little easier to write the converse. Now, if we were to write this as a biconditional statement, if both of these were true, then we could write it as a biconditional statement, and we could say, if P, then Q, and if Q, then P. And the shorthand notation for that would be P with an arrow on both sides of the line in between them. And what was it I said that we typically look for in a biconditional statement?
The if and only if.
If and only if. So another way to write this would be let's see, P. I told you my shorthand notation for that is IFF. P if and only if Q. So we could write it. All of those would be the same way of stating that. All right, so thinking about that, let's let P equal this. P equals the value of x is -5. Let's see. Quote, and we're going to say that Q, let that be the absolute value of x is 5. And so now if I told you to write P, if I told you to write this in words, how would you write that in words? Aiden.
If the value of x is -5, then the absolute value of x is 5.
Exactly. Does everybody see that? If you can identify, if you've got phrases like this and you can identify which one is P and which one is Q, then it's really easy to write the conditional statement by just putting the if in front of this and then the comma then in front of this, right? So that's pretty straightforward. Does everybody get that? And so then if they tell us to flip it around and do this, do the converse of that, somebody else take a stab at the converse. Cameron?
If the absolute value of x is 5, then the value of x is -5.
All right. Does everybody agree with that? We just switched it around. We put if in front of this, comma, then in front of this, because it's q, then p. So let me ask you a question though. Are both of those statements true? For the first one, if the value of x is -5, then the absolute value of x is 5. Would you say that's true?
Oh, yep.
That's true, right? So this one's true. What about the second one? If the absolute value of x is 5, then the value of x is -5. False. It's false, right? It may not be true. You got eight to comment?
I was just gonna say it could be 5.
Could be 5, right? So all we have to do is just prove it. We just have to put one, what do we call those? Counterexample, right? So this one counterexample, we prove it false. So this one is false. And so they said the last thing they tell us to do here is to decide whether the biconditional statement is true. And it's not, because this one's false. Both of these things would have to be true in order for the biconditional statement to be true, right? So the biconditional statement of this is also false. And how would I say the biconditional statement of that? Somebody else hasn't answered something yet. Give it a shot. What's our key term we want to use in there?
If and only if.
If and only if, right? So you do something like the value of x is -5 if and only if the absolute value of x is 5. But since we can't list both of these as being true, then our biconditional statement is not true. Any questions about that? Well, we've got some other examples that we'll try for this, but I just want to make sure that I haven't lost anybody. Everybody appears to be awake still at this point. Just barely. All right, so let's move on. Let's just talk about another symbol that you need to be familiar with. And it's the negation symbol. So the example they have here, we have a statement, angle 3 measures 90 degrees. And the symbol we're going to use for that is P. But if we negated that and said angle 3 does not measure 90 degrees, then we would negate that by what we call a tilde symbol, a little squiggly line. It's like the little squiggly line we put over an equal sign whenever we're saying that something is congruent. Right? It's the same symbol, but just all by itself. So if you see that symbol all by itself, then it means negation. And why do you think we need to know that? If we're learning symbols for conditional statements and converse statements and biconditional statements, why do we need to know a symbol for negation? Because what else did we learn to write in addition to conditional statements and converses? Huh?
Negative statements.
Yeah, well, like what? Give me an example.
Inverse and contrapositive.
Exactly. So we had to do the contrapositive and the inverse, all right? And so what this means is that if you think about the way that we do the inverse, if I say P, if P then Q, then the way that I would write the inverse of that would be, you negate both sides, right? Tilde P, tilde Q, like that. And then the converse, we said, was you flip them around and you say if Q then P, and so the contrapositive is the negation of the converse. contrapositive, and that is negate the Q and then negate the P. Right, so if we've said that P equals it is raining and Q is that the soccer game is canceled.
Oh no.
What's that? Bummer? It's a bad day? Yeah. Yeah, it's a bad day when the soccer game is canceled. It asks us for the, if we write our original if then else, if then statement, then we would say P, if P then Q. And they said write the contrapositive of that. What would the contrapositive be of if P then Q? What do we want to write first if we're going to write the contrapositive? Looking for a hand that I haven't seen yet. Do the rest of you guys have hands? I haven't checked. Everybody verify. Let me see. We already have a hand. I don't want to pick on somebody that doesn't have. He's like, Mom, he's always asking me to show my hand, and I don't have a hand. No one in here is like that, right? Okay. Good that. All right. What do we find if we're doing the contrapositive? Remember, the contrapositive is the negation of the inverse, right? So first we have to write the inverse of this. So what would the inverse be?
So that'd be
The inverse we just,
tilde P.
well, for the inverse, I didn't mean to say the inverse. Did I say the inverse?
Uh-huh.
Pardon me. I meant to say the converse.
Oh, it's Q, P.
Right. So it's just Q, if Q then P. So somebody else with hands, tell me the contrapositive. It's written on the board. It's really easy. The contrapositive, Piper?
I don't know if I have this right, but if it is not raining, then the soccer game is not canceled.
If it is not raining, then the soccer game is not canceled. All right, so what she just gave me was this here. Does everybody agree that that's that? All right, so she took this statement and she put a knot on it and negated it, and then you took the statement and put a knot on that, right? And so that is what? That's the inverse, yep. So now reverse that. Give it to me as a contrapositive.
If the soccer game is not canceled, then it is not raining.
There you go, exactly, all right? Does everybody see that? And so the way that I would write that down in symbol form is I would say tilde Q tilde P. So she's right. If it is not, that's the key there, if the game is not canceled. If the game, I'm going to leave soccer out because this is any game. This could be any game, right? I mean, not all of us play soccer, okay? If the game is not canceled, then, actually it's just because I didn't leave enough room on the board for soccer. But if the game is not canceled, then it is, again, not raining. So you guys see how the symbols can kind of help us if we know if we can kind of identify, if we've got an original statement, we can say, okay, this is our P and this is our Q, then it's really easy for us to think about these things as just, it was kind of hard to write down the long, box before, where we had original and, and then we had the inverse, right? And we had the converse, and we had the contrapositive. But if we can identify P and Q, now it's really easy for us to just say that's that, that's that. This is that, and then this one is that, right? So that's like perfect size to fit on your index card, right? You can figure out P and Q. Nice, Jackson. Is that going to keep down the temptation of waving at people outside?
Absolutely.
Okay, nice, excellent. So does everybody follow that? Right? Just identify P and Q and just think about those, and it's really easy to write the contrapositive and the inverse and all that stuff. All right, so one final thing that we need to talk about in this section here is the law of detachment and the law of syllogism. You're like, really? I thought this was a math class. Doesn't seem like it. So, law of detachment. Now that we've got our symbols, we can give a nice, concise definition for the law of detachment. By the way, how did you guys think the index card worked on your test? Did that work out pretty well for you?
Great.
Cool, excellent. So if the law of detachment says this, if P then Q is true, and P is true, then we can conclude Q is true. If P then Q is true and P is true, then Q has to be true. And so if we think about our example here, and we say that if it is raining, then the soccer game is canceled. If that's true, that's a true conditional statement, and it is raining, then what also has to be true? Then the soccer game's been canceled, right? So the law of detachment is just why do we need to know that? Because whenever we start doing proofs for these different statements that we're making in here, we might sometimes say the reason this is true, the reason we can assume that I can draw this conclusion is because of the law of detachment. So you need to understand what that means. Any questions about that? Any questions, Annalie? No? Okay, all right. So, do you remember what my name is? Okay, all right, so checking. I know you're bad about forgetting that. So, all right. So let's talk about the law of syllogism. That's our other law in this particular section. Law of syllogism. What was the other person's name that I forgot? I know where she sits. I'm just trying to remember what her name is. I forgot your name, right? Did I forget your name?
Oh,
Don't tell me your name. I know it. It's Grace, right?
Yeah.
All right. I think that's the only ones. I think those are the only ones I forgot today. I'm glad Kylie wasn't here because I cannot see Kylie's face at all right now. All right.
She was here.
Huh?
Turns out she is.
Law of syllogism. It says this: if P then Q, all right? And if Q then R are both true, then we can say if P then R is also true. So the law of syllogism is a way to prove that.
That's like saying, that's like a line segment. If A and B, well, it's hard to explain. If A and B equal one thing, and B and C equal one thing, then you can put A and B together, or A and C together.
Well, let's think about it from, it's kind of that idea. But let's think about it, let's see. For P is it is raining. Q is the soccer game is canceled. R is we go get coffee. All right? Because it's sort of on my brain since somebody brought some coffee in and didn't share. So, yeah, exactly. You guys aren't helping with a little all, you're making me feel worse. All right, so let's think about that. So if it is raining, then the soccer game is canceled. And if the soccer game is canceled, then we go get coffee. So, what does the law of syllogism say?
It's raining and we go get coffee.
If it is raining, we go get coffee. I like that, right? It's kind of cool because it's like whether the soccer game is canceled or not, I have an excuse to go get coffee as long as it's raining, right? Does that make sense? You guys see how you can connect those dots? All right. So let's try an example here in the book from zoology. And did somebody make like a weird noise when I said zoology? Is it like, ooh?
It's like biology, zoology.
So, yeah, it sounds cooler than biology, right?
Yeah.
It's got a zoo in it. So let's just do one. They ask us to use the law of syllogism, and we're going to use the first two statements. So here's the first two statements. If a bird is the fastest bird on land, then it is the largest of all birds. And then number two conditional statement says, if a bird is the largest of all birds, then it is an ostrich. So use the law of syllogism to give me another conditional statement based on those two. If a bird is the fastest bird on land, then it is the largest bird of all birds. And if a bird is the largest of all birds, then it is an ostrich. Let's see, I don't think, Camille, you've said much today, so let me hear.
Okay, so if the bird's the fastest of all on land, then it's ostrich.
Then it's an ostrich, right? Exactly. So she took the first part of conditional statement 1 in the book, this is on page 90, and she took the last part of conditional statement 2, using the law of syllogism, she was able to put those together. Does that make sense to everybody? All right. So, if it's game day, Alabama is playing, right? We could say that. So make a statement like that. I'm not going to take that any further. That would get too many. That'd be like pouring salt. There was going to be a conditional statement with Texas A&M in there, but I'm not going to go there.
You're going to mention.
All right. So any questions about that, the law of syllogism or the law of detachments? You guys got that? All right, cool. You know, that totally wouldn't work with your glasses if you were wearing progressives. Because you'd have to like look the wrong direction. No. So they gave me progressives. They gave me these weird progressives last time I went to, I've never had progressive glasses before. That's where like, you know, it like progressively changes. So, because I can see far away in one eye and I can see up close in the other. So it's really bizarre. So it's kind of a good thing, right? It means that I can basically see everything, but it's like the older that I've gotten, you kind of reach this thing where you're like holding stuff out, you know, to try to see it. So they were trying to give me some glasses to help with that, so that I could like read this easily and also see you guys. Man, I cannot do it. It's just the whole progressive thing is. It's like I have to tilt my head like this, you know. So be looking at you guys this way. That's not right.
Oh, it's weird.
Yeah. And so they tell me the glasses are right. It's just maybe my head's just all, you know. I'm like, I'm not symmetrical.
you with
Okay, so let's move on then. Yeah, I just want to go. I'm going to start the next section. I don't think we'll get through with the next section, but I want to start it because this is where we kind of get into the meat of what we're going to be doing throughout this course. We're going to be talking about some properties here that I'm going to, like, way down at the end. These are going to come up again in a chapter, right? So this is why your index cards are going to be so important. Don't throw your index cards away, all right? Somebody stapled their index card to the test, and that's cool, that's fine. And I wouldn't mind kind of seeing how you've organized it. Maybe I could give you some pointers on that. But I'm going to give that back to you, whoever it was that gave me that index card, because you're going to want those for future tests. You're going to want to be able to go back to those, and you might want to transfer some stuff over, right, to whatever the next test is, depending on what we've done. And these properties are one of those things that if you don't, at some point you may begin to commit them to memory. That's sort of my hope. And then you won't have to include them on your index cards going forward. But you might find that you need these down the road, all right? So we've got some properties from algebra, some properties that we already know. And I'm just going to, these are on page 96. This is chapter 2.4. And so we're going to do the addition property. We've got the subtraction property. The multiplication property. And anybody want to take a guess what the next property is?
Division property.
The what? Okay, that's it. The division property. And so these should be very familiar to you, right? We use these all the time. It's just the way that you've written it here may not be obvious. If A equals B, then A plus C equals B plus C. And we could say the same thing with subtraction. If A equals B, then A minus C equals B minus C. And we could say if A equals B, then AC equals BC. And if A equals B, this one we have to say, and C doesn't equal 0.
Why would we have to say that?
Because we're about to say then A over C equals B over C, and you can't divide by 0.
Cool.
All right? Alright, so before I move on to these, let's talk about these just a second. You already know these. So this is why we're able to do something like this. X minus 3 equals X plus 5 at 2X plus 5. Alright? And so let's say we want to solve for X. And so how would we do that? Well, we would get all the x's on one side, and we would get all the numbers on the other side. And so like if I move this, let's say I move this x over here, so that I've got my x's over here and they're positive, I would say negative 3 equals 2x plus 5 minus x. Does everybody agree with that? All right. Well, the reason that we could do that is because of the subtraction property right here. Because what we actually did is we subtracted x from this side. And since we said this side, if we think of this side as being A, and we think of this side as being B, then A equals B in this equation, right? And so we subtracted an x from this side, and so that means that that's going to equal this side with an x subtracted. And when we did that, the x's canceled out over here, and we were able to move our x over, right? So that's the subtractive or subtraction property. So we could do that. We could do some more of that. We're going to move the 5 over here, and that would also be using the subtraction property. And so now we've got -3 minus 5 equals 2x minus x. So we use the subtraction property again to do that. We could combine our like terms, and so we say -8 equals x. And I didn't mean for us to be done that quickly. Let's say we don't make this a 2. Let's say we make this a 4. All right. Not a 4. We make this a 5. 5, 5, 5. So this becomes a 4x. All right. So now we can use the division property to solve for our x, right? Because since if this is A and this is B, and A is equal to B, then I can divide by some value C, which we're going to make C be 4, and say that that's also true, right? And so that gives us the ability to say then that x equals -2. Okay, so these are the properties that we use to do those kinds of things when we're rearranging equations algebraically, right? But we're going to use these in some of our proofs in the future. And like I said, I mean, all the way down, like multiple chapters down, we may come back and reference these. So just begin to commit that to memory, that's what we call that when we use those types of properties to rearrange our equation algebraically. Anybody have any questions about that?
So would it be a good idea to put like some of like the ones that if you didn't commit it to memory on your card?
Yeah, exactly. Yeah, maybe the first time, maybe this first test you want to put these on the card, and maybe you'll be using them enough going forward that at some point you just don't put it there. Or if you put it there, it's a really tiny note that just is like, okay, addition property, A plus C, maybe you don't write the whole thing out. Maybe you just figure out some way to, a little quick note to just jog your memory. Or maybe you don't write these down at all. Maybe you just write down addition, subtraction, multiplication, division property, and you know what that is once you've used them over and over again. Because what you're going to give me whenever you're doing a proof, if you're trying to prove, like we might have something in the future where you've got a figure, maybe a triangle, kind of like on our test, and I'm telling you to prove to me that angle A is equal to angle B. So you're going through all these steps to prove to me that that's the case based on the information that I've given you. And so you might throw in one of these properties, and you just say, I know this is true because of the multiplication property, right? You just tell me the property name. That's all you have to give me when you're giving the proof. All right. So let's talk about the reflexive property and the symmetric and the transitive property real quick. This just says for any real number A, then A equals A. And I know, you look at that and you're like, duh. Right? For any real number A equals A. So if I have 2, you're telling me I can say 2 equals 2? I know that. Right? But there's a property that states that.
But what if 2 wasn't 2?
What if 2 wasn't 2?
What if 2 equaled 3?
Well, and that's kind of, okay, that's going too far. Out of my class. Right? Now, where this comes into play is where you have something like this. A equals 2 and B equals 2. Okay? And so then you can make the statement that A equals B because of the reflexive property.
Got it.
Does that make sense? That's where we'll use that in the future. For the symmetric property, if A equals B, then we can flip that thing around and say that means that B also equals A. So there'll be some things in the future where we have to know that.
Whoa.
And, right, I mean, that's just like when I write this here. if I tell you to give me what the value is for x, you could take it down to here, or maybe you took it down to right here. Maybe when you got to right here, you're like, you know what? I like my x's to be on the left side, so you just take this thing and you flip it around right here. And that's no problem, right? You can do that. What do we call that property that means that we can do that with equations? Well, we call it the symmetric property, okay? And the transitive property says this: if A equals B and B equals C, then we can say A equals C. One final property I'm just going to write down. And again, this will just save us some time next week so that we're not having to go through these again. You'll already have notes on it. These are not going to be on the test. Okay, so our quiz next week will not cover this. I'm just kind of getting us ahead of the game so that we can get through 2 sections next week. The substitution property says if A equals B, then A can be substituted for B in any equation. And so that's kind of like on the test. Had I given you, had I done number 1 right, not had the typo on number 1, and said that what I was trying to get you guys to, if I'd given you that AD was the length that I wanted you to tell me, AD was the total length, AD was equal to 39, that's what I meant to say. You remember that one there, we had AB, I said was congruent with BC, and so then when I put that into an equation where I was saying like AB, the length AB plus BC, or actually this was, I think it was CD, sorry, this was CD maybe? So I said this plus CD, all of that equals 39. I said because these are congruent to one another, because AB equals CD, then I could just replace one for the other. I could say then that AB plus BC plus AB equals 39 and change it to 2AB. So it's the substitution property that allows us to do stuff like that. Because we know one is equal to the other, so we can just substitute in one for the other. Okay? Does that make sense to everybody? You good? You sure you're cool with that, Grace? You got it?
Yeah.
Okay, all right, nice. I think your names were the only ones I was kind of struggling with today, so I'm getting better. As long as I know you guys next week, So, all right, y'all have a good day, and let me know if you have any questions. Your assignment, I'll put your assignment online.